In this lesson, we're going to be proving or verifying trigonometric identities. We want to look first of all at a few suggested ideas about solving these trig identities. Then we want to review some algebraic concepts, and then we'll actually get into looking at some proofs or verifications of these trig identities. Before you start this lesson, you should have had already a lesson about the fundamental trig identities. We will be reviewing those as we start out this lesson. I have listed here several suggested steps or things to consider as you verify trig identities. Notice that the very first thing that we talk about is to memorize fundamental identities. You must memorize these identities. You must know them as well as you've learned things in the past, like 2 plus 2 equals 4, so that you may recognize things as you're trying to verify these trig identities, and it will make the problem much easier for you. Notice number 2 says also to be able to recognize alternate forms of the fundamental identities. So sometimes it's not just enough to know the identities themselves, but to also recognize other forms. Now, before we look at these other steps, I want us to look at the fundamental identities and review those so we're sure exactly what identities we're talking about here. Notice that the first fundamental identity I have written is cosecant theta equals 1 over sine theta. These first three identities that you see here are referred to as the reciprocal identities. We recall that cosecant is the reciprocal of the sine function. Secant theta equals 1 over cosine theta. Cotangent theta equals 1 over tangent theta. Most people remember this third one really easily, but I always have students that confuse these two. So you want to be sure and work on these first two and make sure that you really remember which is the reciprocal of which. One thing that I do is to notice that cosecant and sine, notice we have the C and the S, and then on secant and cosine we have the C and the S. So if I'm looking for the reciprocal of cosecant, I know its reciprocal is going to start with an S, and that helps me to remember and distinguish between these two. We also have the quotient identity, tangent theta equals sine theta over cosine theta, and of course the companion quotient identity here, cotangent theta equals cosine theta over sine theta. It's been my experience that most students also remember these two quite well. Then notice in this upper corner we have our negative angle identities. Sine of negative theta equals minus the sine of theta. The cosine of negative theta is equal to just cosine theta. And the tangent of negative theta equals minus the tangent of theta. The way I try to remember these is to think about the quadrants and the sign involved in the quadrants. If I have a negative angle, I sort of picture a fourth quadrant angle, although it doesn't necessarily have to be fourth quadrant. But I realize that in the fourth quadrant the sign is negative, whereas in the first quadrant it's positive. So if I'm doing the sign of a negative angle, that has to be negative, and of course it will have the same numerical value as the sign of that positive angle. Of course the cosine is positive in both the first and fourth quadrants, and so we see that relationship here. These identities, although they're used, are not usually quite as often as the ones that you see here, and so sometimes students forget about these identities, but when you need one, it's essential that you remember what that identity says. And then finally on our list of fundamental identities we have what we call the Pythagorean identities. Sine squared theta plus cosine squared theta equals 1. Most students remember that one really well. Tangent squared theta plus 1 equals secant squared theta. And 1 plus cotangent squared theta equals cosecant squared theta. So if you've not already memorized these fundamental identities, I would suggest that you perhaps pause your tape and spend a little time going over those, and for sure be sure that you've memorized these before you try to do your homework or you try to do an examination on verifying identities. Now I want to mention just a little bit about this recognizing alternate forms. For instance, down here this sine squared theta plus cosine squared theta equals 1. Notice if we subtracted cosine squared from both sides of this equation, I would have sine squared theta equals 1 minus cosine squared theta. you will see this occurring quite often, where you'll want to replace 1 minus cosine squared with sine squared. Of course, you could also subtract the sine squared and have cosine squared theta equals 1 minus sine squared theta. These two are alternate forms of this identity here, and you'll want to work on those. Notice on our tangent squared theta plus 1 equals secant squared theta. If I subtract the tangent squared, 1 is equal to secant squared theta subtract tangent squared theta. So another alternate form. Of course, you could also subtract the 1 and have tangent squared theta equals secant squared theta subtract 1. Now, it's not my purpose on this tape to go through all of those alternate forms, but you do need to be aware that sometimes we do see these identities written in another form, and we need to know these identities well enough that we recognize that. Now, back to our steps. Besides having these fundamental identities memorized and able to recognize alternate forms, notice number 3. Look for algebraic operations that could be performed. Now, this may include addition, of course, subtraction also, factoring. You'll find that many times we can accomplish what we need by doing factoring, and there would perhaps be other algebraic operations, multiplying, those sorts of things that we might do to change the way that a problem looks. When we do these algebraic operations, we have to, of course, follow the rules from algebra. For instance, if we add two fractions, then we must have a common denominator and those sorts of things. I believe as we work through our identities, you'll see how we use these algebraic operations. Number 4 says to try to simplify the more complicated side. Usually it's easier to simplify something than to make it more complicated. So a lot of times as we approach these identities, we will identify which side looks more complicated to us, and then we will start working on that side and try to accomplish what we're trying to prove. Keep focused on the goal. Every once in a while you may want to look back up there and say, now exactly what am I trying to show here, so that you can maybe make a better choice about what you could substitute or what you could do in terms of an algebraic operation. Again, we'll talk about focusing on the goal as we prove our identities here in a little while. And then 6, I've just said learn tricks such as using conjugates. Now, these are not really tricks. I sort of refer to them that way because they're perhaps things that we might not think about doing on our own, but because they are algebraically correct and that we can do these things, it does help us to get what we need. And so one of the things is using conjugates. I'll point that out in one of the problems when we do that to change the form of an answer. Now, these tricks, as I said, are not really tricks. They're real things that we can do, but they may not be things that you would have thought of on your own. So it's going to be important as you look at this lesson that you consider the things that I show you, and then later on as you're approaching a problem you might say, well, I wonder if that trick might work here to rewrite my problem. Now, before we actually get into verifying identities, I want us to look at some sorts of algebraic type operations that we can do involving trig functions, just to get you thinking in terms of using algebra to work with trig functions. This first one says to perform the subtraction and simplify. Notice we have two fractions, 1 over cosine x plus 1. We're subtracting 1 over cosine x minus 1. Now, the trick here is to look at the trig function the way you used to look at a variable. In other words, if this cosine x right here was, say, the variable y, then this would be sort of like having 1 over y plus 1 subtract 1 over y minus 1. This cosine x is just like having a single variable. Remember, cosine x is an entire quantity. We can't separate the function name from its argument. So thinking about a problem like this from algebra, we would get a common denominator of y plus 1 times y minus 1. So to do this subtraction, we're going to get a common denominator, and our common denominator will contain the factors cosine x plus 1 and cosine x minus 1. So I'm going to come down here. We will be creating new fractions. My common denominator, we've already said, is going to be cosine x plus 1 times cosine x minus 1. So you'll know I'm preparing two fractions here with that common denominator. So now sometimes you'll be able to combine this step with another step, but I want to be sure that everybody follows this step right now. Okay, looking at this first fraction, if I want the denominator to be cosine x plus 1 times cosine x minus 1, then I need to multiply this denominator by this factor of cosine x minus 1, which means I also need to multiply the numerator by cosine x minus 1. So since my numerator is a 1, when I multiply by cosine x minus 1, I get cosine x minus 1 in the numerator, and of course the product in the denominator. Okay, we've got our subtract sign here, and then we'll look at this fraction. If I'm trying to produce this denominator, then this factor needs to be multiplied by cosine x plus 1, which will mean the numerator also will be multiplied by cosine x plus 1. And so again, because of the 1, we would have these two fractions. Now, we are subtracting. We have a common denominator here. So let me bring the common denominator down. And remember, when we subtract, this negative is going to distribute across this parenthesis on this second one. So minus cosine x minus 1. Okay, you can remove this parenthesis here. So notice we have a cosine x minus a cosine x. Those will cancel out, won't they? Minus 1 is a negative 2. Now, you may think that we're finished at this point, but notice my instructions said to also simplify. We have performed the subtraction, now we're going to simplify. So let me bring this negative 2 over, and let's multiply these two factors out here in the denominator. Cosine x times cosine x is cosine squared x. Notice, because these are what? These are conjugates. They're just alike except for the opposite signs here. The outside product and inside product will drop out. Positive 1 times negative 1 is a negative 1. Now, think about this, cosine squared x minus 1. Remember, a second ago we were looking at this alternate form, sine squared theta equals 1 minus cosine squared theta. Well, see, this is sort of like that, except my signs are sort of backwards. So what I'm going to do is I'm going to factor out a negative 2 down here in the, a negative 1 down here in the denominator. That will make that a plus 1. And a minus cosine squared x. So notice my negatives cancel. I have a positive 2. 1 minus cosine squared x can be changed to sine squared x. And then, since sine squared is the reciprocal of sine is the reciprocal of cosecant, 1 over sine squared is the same thing as cosecant squared. So 2 over sine squared would be 2 cosecant squared x. And so we simplify very nicely down to that single trig function right there. Now, first of all, what's important is the algebra. We're doing the subtraction, common denominator, combining numerators, bringing over the common denominator. Then we did a little bit more algebra here in terms of multiplying that denominator out. But once we got to this step, if we don't recognize that this denominator is sort of an alternate form of my sine squared plus cosine squared equals 1 identity, then I won't be able to do the further simplification that I need to do here. That's why we want to be sure and learn those identities so well that that's sort of jumping out at us, that we see that. In this next problem, it says to multiply and simplify. Notice here we have a quantity squared. Now this problem is similar in algebra to something like this, a subtract b quantity squared. We know, of course, to square a binomial, we square the first term. We multiply the two terms and double, so we'll have a minus 2ab, and then we square the last term. So we're going to do that same process, but we'll do it with these trig functions. So if I square my first term, I have cosine squared x. Then we're going to multiply these two terms and double the answer. So a minus sine times a cosine doubled is minus 2 sine x cosine x. And then finally, we're going to square this last term. If we square a negative, we get a positive sine squared x. So we've done the multiplication. Now we need to simplify. To simplify this, do you see this cosine squared x plus sine squared x right here? Well, of course, because of commutative property, we could rewrite this, but instead of rewriting it, we're just going to look at this and say, well, hey, I know cosine squared x plus sine squared x is a 1, isn't it? So I'm going to replace that with 1, and I'll bring down the minus 2 sine x cosine x. And that would be our simplified form of this answer. So again, we're doing some algebra, but then we're recognizing our fundamental identity here in order to simplify. I have one other little sort of practice problem here before we get into verifying the identities. This says to factor, okay? And you'll notice these are not equations or anything. We're just asked to factor. So again, think back to algebra. 4 sine squared theta plus sine theta subtract 3. This is exactly like having a problem like 4x squared plus x minus 3. See this sine theta here, sine theta here? The sine theta is the same trig function, so it's just like having the same variable. Notice though one is squared and one is not. Now, to factor this, we know that we would look for two terms whose product is 4x squared. And so that might be 2x times 2x or 1x times 4x. And I'm sort of looking ahead here. I'm going to put down 4x times 1x here. We know that our third term dictates the numbers that go here, so that must be 3 times 1. And because of the negative on the 3, I know these are opposite signs. Notice if we put a 3 in that factor with the 4 and 1 over here, we have a 4x for the outside product, 3x for the inside. If we put our positive over here with our 1, we have a plus 4x, put the negative here, minus 3x is 1x, and then we have our negative 3. So this problem is going to be exactly like this, except in place of x, we're going to have this trig function sine theta. So since we've already done the work over there, I'm going to write 4 sine theta, that's a minus 3 times sine theta plus 1. Now let's look at this. If I multiply 4 sine theta times sine theta, I get 4 sine squared theta. Notice my outside product is a positive 4 sine theta. Inside minus 3 sine theta, that gives me 1 sine theta, and then minus 3. So this again is just like the algebra problem, except our trig function has taken the place of that variable. Now this next one is one you may have forgotten, is the reason I put it on here. Sine cubed alpha plus cosine cubed alpha. Do you remember x cubed plus y cubed, how you factor that? If you've forgotten that, you may need to go back and pick up the factoring tape and review factoring sum and difference of cubes. This will factor into x plus y times x squared minus xy plus y squared. The process is you take the cube roots of these terms, same sign as what's between them, and then you work from your factor here. Square what you wrote down, opposite sign to this one, multiply these two, notice here there's no doubling, and then square the last one. So we're going to apply that here. My cube roots would be sine alpha and cosine alpha, and because my problem has a plus sign, I'm putting a plus sign between those. Now, for our second factor, we're going to square what we have here, so that will be sine squared alpha, opposite sign, multiply these two, so I have sine alpha times cosine alpha, and then we square this last one plus cosine squared alpha. Now we have this thing factored, but I want to notice something right here. See that sine squared plus cosine squared? What can I do? I can change that, can't I? Sine squared plus cosine squared. What does that give us? We're going to have 1. Sine squared alpha plus cosine squared alpha is 1. So I'm going to simplify this second factor. And I have sine alpha plus cosine alpha times 1 minus sine alpha times cosine alpha. And then finally, this last one should be more clear. Tangent squared beta minus cotangent squared beta. This is a difference of squares. Remember, when you factor a difference of squares, you get conjugates. So I will have tangent beta plus cotangent beta times tangent beta minus, oops, I wrote tangent again, then I'm saying cotangent beta. So tangent beta plus cotangent beta times tangent beta minus, that's cotangent beta here, okay? I hope that what you're seeing here is that we can do algebra just like we've always done algebra, but we're thinking about that trig function like we used to think about the variable x or y. And then we're going to get into verifying identities. I have a reminder here that I'm going to put up on the screen and talk about, because this is very important when you start working with identities. Remember, verifying identities is not the same thing as solving equations. You need to remember that we are not solving equations. When you do the same thing to both sides, you are keeping equals equal. Remember, when you solve equations, you would add the same thing to both sides or multiply both sides by the same thing. That was allowed because you were starting out with an equation, a statement of equality that you knew was true. And basically you were saying, if this is true, then if I add 5 to both sides, it's still true. That's kind of what we were doing when we solved equations. But notice, when you're verifying an identity, you are trying to show that one side is equal to the other. You don't know that they're equal, you're trying to show that. So you must work with only one side at a time. You can't add the same thing to both sides or whatever. You must show that one side can be transformed into the other using known identities, that would be our fundamental identities, and true algebraic operations. You may also show the two sides are equal to a common third side and thus equal to each other. This is the key. Work with only one side at a time. Don't be tempted to do the same thing to both sides when you're solving or verifying these trig identities. Now we're ready to look at some actual identities that we want to prove. And so we're going to start off with some that are not quite so difficult, and we will work up in difficulty to some others that become a lot more complicated. As we go along, I will be suggesting things to you to try. Now, I also want to point out to you that a lot of times there is more than one way to verify an identity. So I may verify this identity one way, and you might say, well, I wonder why she didn't do this. Well, you might try that on your own, and you may find that if you did whatever that was that you saw to do, that it might also work. The point is, we're just trying to take one side and, using fundamental identities and algebraic operations, transform it into the other side so that we know the two sides are equal. Okay, well, let's go to the identities and see what we can do with them. Verify the following identity. We have tangent alpha divided by secant alpha. We're trying to show that it is equal to sine alpha. Now, a lot of times I will suggest this. We don't know, even though this says equal right here, if it's saying to verify, it's saying, does this equal this? So I'm going to suggest, let's start out with a question mark there. We want to know, is the tangent of alpha divided by the secant of alpha equal to the sine of alpha? Now remember, one of the steps that I suggested to you, I'll put it back up here, was to try to simplify the more complicated side. Okay? So let's look at this thing. This side with the fraction is more complicated than this side with just a sine function, isn't it? So I'm going to start with this complicated side, tangent alpha over secant alpha. Now you'll notice I'm only going to start with that one side, and I'm going to see what I can do to this to transform it. Now, just looking at the problem, I don't see any algebraic operations to do. So I have to think about, are there any fundamental identities that I might use to change these functions into something else? Well, let's think about tangent. Well, let's see. I know that the tangent is the sine divided by the cosine. So I may replace tangent alpha with sine alpha divided by cosine alpha. Notice that's now in my numerator. Well, what can I do with the secant? Think about those reciprocal identities. The secant of alpha is 1 over the cosine of alpha. Now, one reason that I thought to do that is I really didn't have much else that I could do, but another reason that you might think about is to look at what we're trying to get. We're trying to get down to just a sine of alpha. So by changing into sines and cosines here, I have an opportunity for things to drop out perhaps and get to that sine alpha thing. Now, of course, what we've created is a complex fraction. But this just means this fraction is being divided by this fraction, isn't it? So we're going to do some algebra here. I'm just going to write down, and I'm going to put in this step. You could probably skip it for most of you. But we're saying that sine alpha over cosine alpha is being divided by 1 over cosine alpha. See, that's a legitimate algebraic operation. Well, how do we divide fractions? We invert the second fraction, don't we? And we multiply. So let's do that. Times cosine alpha over 1. And of course, at this point, we can see that our cosine alphas will cancel. We have sine alpha over 1, which is simply sine alpha. So notice what I did. I took the left-hand side, and by using identities and algebraic operations, I have shown that it is equal to this other right-hand side. And so I have verified that these in fact are equal. All right, well, let's take a look at another identity. Verify the following identity. Cotangent x plus tangent x equals secant x times cosecant x. Now, again here, that's a question mark right now. We don't know, but we're trying to prove that these are equal to each other. Now, as far as which side is more complicated, it may seem to you that they're about the same. So another thing I consider is that one of the steps suggested doing algebraic operations. Well, I know that there's something I can do to add things together, particularly thinking ahead a little bit that these can be written as fraction forms, can't they? And so I think I'm going to approach it by taking this left-hand side of cotangent x plus tangent x, and first I'm going to use my quotient identities. Cotangent is cosine x divided by sine x, and I'm adding the tangent function is the sine of x divided by the cosine of x. So again, using fundamental identities, I've transformed this, but now I'm adding fractions, and so I need a common denominator here. Well, my common denominator is going to be sine x times cosine x. Now this time I'm going to see if we can accomplish this on one step. This first fraction, to get sine x times cosine x, I would need to multiply this denominator by cosine x, wouldn't I? So I'll also multiply the numerator by cosine x. So I have cosine x, I'm going to do this for emphasis, times cosine x. Okay, now I'm going to go ahead and put my plus sign here. And this fraction, to get my new denominator, I'd have to multiply by sine x. So I'm going to have my numerator of sine x multiplied by another factor of sine x. Now, multiplying this out, I have cosine squared x plus sine squared x being divided by the product sine x cosine x. Now, usually students spot this pretty quickly. What can I do with cosine squared x plus sine squared x? That's 1, isn't it? So I have 1 over sine x times cosine x. Okay? Now, I don't always write this step down, but this first time for emphasis, I want us to understand that this 1 over sine x cosine x could also be written this way, 1 over sine x times 1 over cosine x, because when we multiply fractions, we multiply the numerators and the denominators. So thinking about this product in this form, I know that 1 over sine x is what? Cosecant x. and 1 over cosine x is secant x. That's using my fundamental identities. Now let's look at this. Cosecant x, secant x, that's a product, so it can be written in another order, equals secant x times cosecant x, which is my objective, what I wanted to try to show. Look this over and see if you have any questions concerning the steps that we took. Quotient identities, to write it like this. We got a common denominator and added our fractions. We used a fundamental identity to get 1. We reasoned that this could be written as this product, which gives us these trig functions, and then we can, of course, put products in any order that we want them. Verify this following identity. 1 minus cosine squared times 1 plus cosine squared x equals 2 sine squared x minus sine to the 4th x. Well, I'm thinking a few things ahead of time. Again, of course, we don't know for sure yet that this is true. We're trying to prove that. But I always kind of analyze a few things. Notice over here I have cosine functions. Over here I have sine functions, don't I? So one thing might be to consider, if I start over here, I have several possibilities. I could multiply these out, or I'm already seeing right here, what's 1 minus cosine squared x? That's sine squared x, isn't it? So that might be a possibility right off the bat to substitute sine squared x for that. So I'm thinking there are some things that I can do, perhaps, to transform from this side to this side. So I think I'm going to start with the left-hand side. 1 minus cosine squared x times 1 plus cosine squared x. And since I'm trying to get this in terms of sine functions, I'm going to go ahead and convert everything that I can think of. Well, 1 minus cosine squared x is sine squared x. And let's look at this other factor. I have this 1, which I'm going to bring down, plus. Well, what can I substitute for cosine squared x? Remember again those alternate forms of our identities. Cosine squared x is equal to 1 minus sine squared x. So I'm going to put that in. Notice this 1 minus sine squared x is replacing this cosine squared x here. Okay? Well, let's see. Let's simplify inside that factor now. I have sine squared x still outside. 1 plus 1 gives me 2 minus sine squared x. Now look at what we're trying to get. We're almost there, aren't we? All we need to do is to multiply by distributing this sine squared x across here. So I have 2 sine squared x minus sine to the 4th power of x, which is exactly what I wanted to show that I was equal. So sometimes I look ahead in the beginning. Are there things I can do to change this into this? And I see there's a sine squared right there. And of course I can replace cosine squared with 1 minus sine squared. So that was the approach that I took. Verify the following identity. Sine to the 4th theta minus cosine to the 4th theta equals 2 sine squared theta minus 1. Of course, again, we're still saying, is this true or not? Now, in analyzing my two sides here, I would consider this side to be more complicated than this one because it has higher powers on it. So I'm going to start on this left-hand side, sine to the 4th theta minus cosine to the 4th theta. And I'm going to need to think about what can I do with this. Now I know I can change sine squareds into cosine squareds or cosine squareds into sine squareds, but notice this 4th power. So I'm going to take a little different approach first. Notice your subtract sign. You are subtracting two things to the 4th power. That means these are difference of squares, right? I can factor this as sine squared theta plus cosine squared theta times sine squared theta minus cosine squared theta. Okay, so recognizing that I have a difference of squares, I'm going to factor. Now look at this factor right here. Sine squared theta plus cosine squared theta is 1. And then in this other factor, I have sine squared theta subtract cosine squared theta. So I have simplified a little bit. Now let's take just a second and let's look back up here at what we're trying to get. Notice what I'm trying to get has only the sine function in it. So that suggests that maybe I should think about that cosine squared right there and rewriting it as a sine function. I can do that, can't I? Let's just drop the 1. We don't need that anymore. And I'm going to go to a bracket here for a second. I have sine squared theta minus, now let's be careful, cosine squared is 1 minus sine squared. So notice that I used a parenthesis. I've got this subtract. I'm replacing cosine squared theta with 1 minus sine squared theta. Now let's distribute our negative here. Sine squared theta minus 1 plus sine squared theta. Notice now I have two like terms, so I may add those. 2 sine squared theta minus 1, which is what I wanted to verify. So watch for difference of squares. A lot of times those will crop up, and seeing this difference of squares allows me to get down now to my second powers. I have a fundamental identity here, and then here I've got one that I can replace also. And then just do a little algebra and simplifying. Verify the following identity. Cosine beta over 1 minus sine beta equals 1 plus sine beta divided by cosine beta. Now, in looking at this, and of course again we wonder, is this true? Both sides are basically almost the same in terms of difficulty. They look basically alike, except one looks sort of upside down as compared to the other one. So on this one, it will not matter which side we choose to work with. So whichever you prefer. I think I'm just going to go ahead and use the left-hand side for now. I have cosine beta, and I have 1 minus sine beta. And you might be saying, what in the world are we going to do with this? Well, this is one of those sort of tricks that I was telling you about a while ago. We're going to do something that's perfectly legal here, but you might not have thought about it on your own. This is what I have, and this is what I'm trying to produce. Now, these don't look anything particularly like, but I notice in what I'm trying to produce, there's a 1 plus sine theta, isn't there, in the numerator? Well, 1 plus sine beta is the conjugate of 1 minus sine beta. And here's the trick that I'm going to suggest here. If you have a fraction, you can multiply the numerator and denominator by the same number and produce an equivalent fraction, can't you? Let me just put some scratch paper up here for a second. For instance, if you have the fraction 2/3, isn't it okay to say times 5 times 5? We were doing that a while ago when we changed denominators. I have 10 over 15. Well, 10 over 15 is just another way of writing 2/3. It just looks different. But the trick is that I'm multiplying the numerator and denominator by the same thing. So as I look at this, if I want to have a 1 plus sine beta in the numerator, well, I can get it there by simply multiplying this numerator by 1 plus sine beta. But if I multiply the numerator by that, I also have to multiply the denominator by that to produce my equivalent fraction. So we're going to take this original fraction and we're going to multiply the numerator and denominator by the same thing, which is legal. Now, I'm going to suggest that for now we leave this numerator factored. The reason I'm suggesting that is because, remember, what I want to have is this 1 plus sine beta, so I'm hoping this guy right here is going to cancel out, perhaps. So I don't want to multiply him through here. I'll have to refactor. Now down here I am going to multiply because I'm hoping something will happen here that will allow me to simplify. So notice I'm going to get a 1, and because these are conjugates, again, this outside and inside product are going to drop out. So I'm going to have a minus sine squared beta, 1 minus sine squared beta. Well, think about 1 minus sine squared beta. That's that alternate form of your Pythagorean identity. So we can replace that with cosine squared beta, which is going to be really nice for us if you're looking ahead here. 1 minus sine squared beta is cosine squared beta. Now look at this factor. We can cancel, can't we? Cosine beta will cancel one of these cosines down here in the denominator, and I will have produced exactly what I wanted to produce. 1 plus sine beta over cosine beta. So the trick, if you will, was to multiply the numerator and denominator here by 1 plus sine beta. I thought about it because that's what I wanted up here, but it's also nice because it's the conjugate of what's down here. That gives me this form right here that I can replace with cosine squared. So as you're faced with other problems, you might think about this same sort of trick now that you've seen it, that you might use that from time to time. Verify the following identity. Sine squared x times secant squared x plus sine squared x times cosecant squared x equals secant squared x. Now, obviously the left-hand side is the more complicated, so we're trying to verify this. I'm going to go ahead and recopy sine squared x, secant squared x, plus sine squared x, cosecant squared x. And we're going to have to decide now, what can I do with this? Well, there's a couple of things that I see that perhaps might work. I see sine squared x as a common factor, so that might be a possibility for me, that I might factor that out. Another thing that I might consider is, because secant squared and cosecant squared have reciprocal identities, I might look at using those reciprocal identities here. I'm going to have to do something, because somehow or other we're going to simplify from this idea of adding these two things together to a single trig function of secant squared x. And guys, this is one of those where whether you factor the sine squared x out first or whether you do the other first, it's going to work for you either way. I think what I'm going to do is just go ahead and I'm going to replace secant squared with 1 over cosine squared, and I'm going to replace cosecant squared with 1 over sine squared and see what happens here. Let me come down this way so we'll have plenty of room. So I have sine squared x. Notice that's times 1 over cosine squared x, plus I have sine squared x times 1 over sine squared x. Now, a couple of things are happening here. On this first one, I have sine squared x over cosine squared x, and if you're thinking ahead like me, that's a tangent squared, isn't it? But look what happened here. That sine squared x cancels, so I have a 1 here. Okay? Well, let's go ahead and change that to tangent squared x. Oh my, do you see what we've got here? Tangent squared x plus 1. That's half of one of our Pythagorean identities. And what does tangent squared x plus 1 equal? That's right, it equals secant squared x, which is what we wanted to get. So this time, just simply replacing these with the reciprocals, simplifying to 1 here and changing that to tangent squared, it worked right out. Now, I also would suggest to you, perhaps you might want to pause your tape here, take you some scratch paper and try what would happen if you factored out the sine squared x and left secant squared x plus cosecant squared x inside that other factor. Would there be something you could do perhaps to simplify that and get back to secant squared x? So that might be a challenge for you. It should work out for you to be able to verify that also that other way. Verify the following identity. Secant theta plus tangent theta divided by secant theta minus tangent theta equals 1 plus 2 sine theta plus sine squared theta divided by cosine squared theta. Wow, both sides are rather complicated here. And so what I might consider doing, and this would be perhaps just my own preference, again, you might choose to do something else, because this side has secants and tangents in it, and this side has sines and cosines in it, I think I'm going to start with this side because I know I can convert these into sines and cosines. And perhaps after I convert into sines and cosines, I'll be able to see how to get to this particular form that I want. So that's going to be my rationale for choosing to work on this left-hand side. Let me get this thing written down. Secant theta minus, that's a plus tangent theta over secant theta minus tangent theta. And I'm just going to go ahead right away and convert. Secant theta is 1 over cosine theta. Tangent theta is sine theta over cosine theta. Down here secant is 1 over cosine theta. This is minus sine theta over cosine theta, isn't it? Okay? Now again, there's several things you could do at this point. You could combine these since these have the same denominator and then invert and multiply. I'm just going to do that a little bit differently. I'm going to multiply the numerator and denominator of this fraction by cosine theta to simplify this complex fraction. So cosine theta times 1 over cosine theta is a 1, plus, here the cosine thetas would cancel and I would have sine theta. And then down here cosine theta times 1 over cosine theta is 1, minus, again the cosines would cancel and I would have sine theta. Now, I've sort of gotten down pretty simple, and you'll notice that I still haven't produced this form right here. So this is a time that I might consider stopping. I've taken the left-hand side, this is the left-hand side, and I've gotten down to this point. And I think what I'm going to do now is to just pause for a second and say, okay, well, let's look at that right-hand side. And I see some things that I might do to this right-hand side. Like I could change this to 1 minus sine squared, and that looks like something I might be able to factor. So here's what I'm going to do. I'm going to take the right-hand side, 1 plus 2 sine theta plus sine squared theta over cosine squared theta. Now you'll notice I haven't worked on the left and right hand side at the same time. I worked on the left a while. Now I'm going to work on the right hand side. Now I can factor this numerator. You need to recognize that's 1 plus sine theta quantity squared, and cosine squared is 1 minus sine squared. So I'm going to make that substitution. Factor the numerator and substitute in the denominator. Now in the denominator I have a difference of squares. Let me bring down my numerator of 1 plus sine theta quantity squared, and I'm going to factor this denominator as 1 plus sine theta times 1 minus sine theta. Now look, this 1 plus sine theta is going to cancel one of my factors up here, and so I have 1 plus sine theta over 1 minus sine theta. Now let's compare. What did I have just a moment ago? Same thing, didn't I? The left hand side is equal to 1 plus sine theta over 1 minus sine theta. The right hand side is also equal to 1 plus sine theta over 1 minus sine theta. So since the two sides are equal to a common third side, if they're both equal to this, they must be equal to each other. So this is true. And of course what we've done is one of these steps that, well, I guess that was not in this, I'm sorry. The suggestion in my little remember thing, there we go. Let me get the right one up here. You may also show the two sides are equal to a common third side and thus equal to each other. So we just did that suggestion right there. Sometimes when these identities are rather complicated, that is a pretty good way. Instead of spending a lot of time saying, how can I change this into this, it's easier then just to go and simplify that right-hand side as well. Okay, well let's take a look at this one. Verify the following identity. I have tangent x over 1 plus cosine x plus sine x over 1 minus cosine x. This is equal to cotangent x plus secant x times cosecant x, or at least I'm trying to show that it is. Now, what could we perhaps do here? Perhaps on the left-hand side, I see that I could perhaps get a common denominator and combine these two. On the right-hand side, looking at here, I could perhaps change to sines and cosines and do something with that, couldn't I? So let's see what we might want to do. I think what I'm going to do is get a common denominator on the left-hand side and work from that point right now. So let me see. Tangent x over 1 plus cosine x plus sine x over 1 minus cosine x. My common denominator will be 1 plus cosine x times 1 minus, oops, I wrote a C there, cosine x. So let's see, my tangent function up here will need to be multiplied by this factor of 1 minus cosine x, plus my sine x, then this second fraction will need to be multiplied by the factor 1 plus cosine x. Okay, can you see that? Alright, let me come back over here. Let's distribute now. I have tangent x minus tangent x times cosine x, and then I have plus sine x plus sine x cosine x. And let's see, I'm going to go ahead and multiply this. That's 1 minus cosine squared x down here. Okay? Wow, looks bad, but let's see what we can do. Tangent x, let me bring that down right now. Tangent is sine x over cosine x. That's times cosine x, so we'll see what happens there in a second. I'm just recopying all this other stuff right now. 1 minus cosine squared x is sine squared x. I'm going to go ahead and put that in. Okay? Now, one reason I'm sort of thinking about that, a cotangent has a cosine over a sine, so at least I'm getting down to a place where I have a sine. Keep glancing up there every once in a while. Okay, notice right here, this cosine x is going to cancel, isn't it? And then look what you have. You have a minus sine x plus a sine x. That'll drop out. So that's great. That's gone. All right, let's rewrite what we have. We have tangent x plus sine x cosine x. These are both over sine squared x. Now, looking at this, notice how up here we have two terms. Well, I'm going to sort of go backwards now. I'm going to split this back apart. I have tangent x over sine squared x plus I have sine x cosine x over sine squared x, right? Okay, well, I begin to see some things that might occur. Sine x over sine squared, I can cancel one of those, right? There's cosine over sine, which is going to be this cotangent I was looking for. Now, I'm going to need a little bit more paper. Let me pull another piece up here. And let's see what we can do on this other side. I think what I'm going to do here, tangent is sine over cosine. And I'm going to write this as sine squared x over 1 plus this cosine x over sine x. I'll rewrite that here in just a second. Okay? Now, here we can flip and multiply, can't we? Sine x over cosine x times 1 over sine squared x plus, I'm going to go ahead and write that as cotangent x. Now, right quickly, let me sort of glance back up here. I wanted the cotangent x first, so I'm going to go ahead and rearrange these right now. Cotangent x, we have that, plus. On the second part, this sine function will cancel one of these. So notice what you have. 1 over cosine is secant x. 1 over sine is cosecant x. So I have cotangent x plus the secant times the cosecant, which is exactly what I wanted here. Now that one got rather long, but notice that we eventually got where we wanted to go. Let's review what we did. We started out, and I chose this just because I saw I can get a common denominator and add these fractions. So that would get me started. And I'm just hoping things will work out. If they don't work out, then you can always go back and try something else. Maybe try working over here. I changed my, or I got my common denominator and added. Then we did a little canceling here, simplifying. Changed 1 minus cosine squared to sine squared. When we got to this point, sort of looking ahead again, I can see these signs are going to cancel. Cosine over sine is cotangent, so I split this thing up. And then I just need to work with this term here. And so we converted that tangent into sine over cosine, flip and multiply, and things worked out. You'll find that as you do these identities, as you try a few things, and sometimes you'll get stuck and realize you're just going in circles and you'll start over. That's okay, because you're learning some from those experiences, even though they're not very pleasant at the time. When you get stuck, you realize, okay, well, I need to go back and try something different, and you get skilled at sort of making better judgments in the beginning sometimes because of those experiences. Okay, let's verify the following identity. 1 minus sine theta over 1 plus sine theta equals secant squared theta minus 2 secant theta tangent theta plus tangent squared theta. Now it appears to me on this one that the right hand side is more complicated than the left, so I'm going to start this time using that right hand side. Secant squared theta minus 2 secant theta tangent theta plus tangent squared theta. Now that's a question mark you were trying to verify. Now again, there's 2 or 3 things you could do to get started on this problem. You can probably factor this like it is right now. That might be good to do. Or because I have secants and tangents here and what I'm trying to get is only the sine function, you might consider going to sines and cosines here. I think that's what I'm going to try to do before I even try to factor, just to see what happens. Secant squared is 1 over cosine squared minus 2 times the secant is 1 over cosine. The tangent is sine over cosine. And tangent squared would be sine squared over cosine squared, wouldn't it? Now remember that 2's over 1 right there. Look, cosine squared here, cosine squared here, cosine squared here. I have a common denominator. So let's just bring all that down. 1 minus 2 sine theta plus sine squared theta is all over that common denominator of cosine squared theta. I didn't even have to get a common denominator. It's there. Okay. Well, now I think I'm ready to do some things. This will factor 1 minus sine theta quantity squared. Cosine squared is 1 minus sine squared. I think we've seen one similar to this before already, haven't we? Do you see what I'm going to do next? I'm going to factor that denominator. So bring down your numerator. And I have a difference of squares down there. So that will factor into the conjugates. 1 plus sine theta times 1 minus sine theta. And of course, one of these factors of 1 minus sine theta cancels, and we have our 1 minus sine theta over 1 plus sine theta that we wanted. So we do get this left-hand side. Now again, you probably could be just as successful factoring here. See, this would factor as secant theta minus tangent theta quantity squared, and then you could perhaps work from there. Okay, I have one more identity that I want us to do in this lesson. Verify the following identity. We have cosine alpha divided by secant alpha plus sine alpha divided by cosecant alpha equals secant squared alpha minus tangent squared alpha. Well, it's sort of a toss-up as far as which side you might want to work on. Let's just start with the left-hand side and we'll go as far as we can. If we don't get the right-hand side, then maybe we'll do that same process we did earlier where we try to get both sides equal to a common third side. But we'll decide as we go along here. Let's see. I think what I'm going to do here, let me change this secant that I have down here to 1 over cosine. And then I've got sine alpha, and this cosecant is 1 over sine alpha. Now, cosine divided by 1 over cosine, you're going to flip and multiply, aren't you? Can you see what's going to happen there? Cosine alpha will be times cosine alpha over 1, and the sine alpha that I have over here will be times sine alpha over 1. Do you see how we're flipping and multiplying? So I have cosine squared alpha plus sine squared alpha, and that equals 1. Well, at least I've simplified this side. I still don't know if it's equal to this side, but I have gotten it down to 1. Ah, look at this thing right here. Seems like I remember an identity, secant squared and tangent squared. Let's go back to that fundamental identity sheet for just a second. Look at this thing right here. Tangent squared alpha plus 1 equals secant squared alpha. Don't forget this identity. If I subtract tangent squared, secant squared minus tangent squared gives me 1, doesn't it? So 1 can be replaced with secant squared alpha minus tangent squared alpha. I can get that side right away. Now, it didn't seem really logical right at first, but if you recognize that's an alternate form of that Pythagorean identity, then you can just get right straight to it, can't you? Now, suppose you didn't see that, and you stopped here with 1. Then what you might do is take this secant squared alpha minus tangent squared alpha, and then use the identity secant squared is 1 plus tangent squared. And notice if you do that and you bring down that minus tangent squared, those drop and you get 1 again. So you could have done that just as easily and shown that the two were both equal to the same thing. I hope that what you've seen in this lesson is that it's very important, first of all, to know those fundamental identities. It helps so much if, as you're looking at this problem, you're recognizing those fundamental identities and their alternate forms. A lot of times that's the whole key, is because of that recognition. The other thing I hope you saw was some of the algebraic types of things that we did to convert one side into the other. And don't forget, absolutely don't forget, you must work with only one side. You can't do the same thing to both sides when you're verifying identities. You only can do that if you already know the two sides are equal. So keep this in mind, and I hope that this will help you in verifying identities. Many students find that that's a difficult thing to do, but others just breeze right through it and they seem to kind of like it. If you approach it sort of like the idea of solving a puzzle, sometimes it makes it kind of fun, and you can feel really good when you sort of find that last piece that makes the puzzle fit together. Thank you very much. I hope that you enjoy this lesson, and I hope that it helps you.